Just as a sort of setting the stage here, this is week 7, so we're getting pretty close to the end of the term. And that's particularly true when you remember that we don't have a week 10. So we have this lecture and 2 more, and that's it. Okay, so today is we're going to finish up on functions, and so that'll be the focus of the day, and then we'll have a lab at the end, which will be focused on functions. And I am going to preference getting through the slides more so than I am time on the lab. Okay, so particularly because we only have 4 people in class, I'm hoping that you'll still have time for the lab, but because we didn't get through all of the things last time, it might be pushing things a bit. So, but there will be lots of time for you to practice in class, just like last time. So I'm going to preference that over the lab. So the lab may end up just being homework. We'll see. So we have functions today, and then the next 2 lectures are both on Shiny. Okay, and we have to use some of that time to review the lab too. And then, week 10, we won't be here, and then your final project is due week 11. So just as sort of a reminder of where we're at, we're starting to get towards crunch time here at the end of the term. All right. So check in with me if you have any questions on that, but that's sort of the plan. Okay. All right, so going back to this example that we talked about, where we were saying, okay, we have these 2 vectors, and we want to write a function that is going to count how many times any 2 generic vectors are NA in the same place. So for example, here, these are NA here, those match, and they're here, those match. So the answer should be 2. Okay, so how do we start to solve this problem? We don't start by trying to write a function. Okay, I've said this a couple of times. I will continue to say this. This is probably the biggest mistake I see people making when they're writing functions, is they immediately go to trying to jump to writing a function to solve the problem. That's going to be way more difficult than if you instead solve the problem on a test case and then use that code you used to solve it on that test case to basically generalize it to a more abstract problem so it can be used on anything. So we talked about this. Just use these actual 2 vectors to see if you can solve it. Once you get it solved, then you can use that code to write a function. So this is one approach. This is the approach I ended up using. You call is.na on the first vector, which I've called A. Call is.na on the second vector, which I've called B. That gives you 2 logical vectors. And then all you're going to do is say and, okay? And that's going to give you a vector in return that is true only when it's true on both of them. So if it's false, true, it's going to be false, true, false, false, true, true, true. Okay, so it's only true if it's true on both of them. And then because of coercion, we can just sum that logical vector, and that will give us the number of trues that we have. Okay? All right. So there it is. Now we want to generalize it to a function. All we do is take that code that we had before, we wrap it in our function code, and we swap out the arguments. Okay, so instead of A and B, I've swapped those out for X and Y. You could call them whatever you wanted, though. You could even call them A and B. However, if your vectors are already called A and B, I would not have your argument names here be A and B, because then that's going to be confusing between what's an object and what's an argument to the function. Okay, so just make them things, whatever it is. All right, so then I said, all right, well, what if they're not the same length though? And in this case, we get what might be some unexpected results. Here, they're obviously the same length, we get 2. Here, they're the same length again, but we basically put them back to back, so we get 4. And then here, they're not the same length. We have A once and we have B twice, but we still get 4. And so that's maybe a little bit confusing. That's because of a concept called recycling. Okay, and so I know I'm going over this fairly quickly, but hope this should all be reviewed. We covered all this last time. All right, so here is recycling. I have the numbers 1 to 4, and then I had the letters A, B. If the vectors are divisible, then the smaller vector will be recycled. So AB, length 2, can go into 4 exactly twice, right? So it gets recycled AB, AB. And so that's what's happening on that previous slide, okay? If they are not divisible, then we get an error, and that's it, okay? So our function that we wrote just previously is fine, right? And there's nothing wrong with it. However, it can have some unexpected results, which we have identified and found. So what should we do? Well, one thing that we could do is we could actually include in our function a check to see if they're the same length. And then if they are, then we continue on. And if they're not, then we stop the evaluation of the function and we provide some error message. Okay, so this is how that basically looks like. We have if some condition, then stop and print out an error message. If this condition is not met, however, then none of this is run and we just skip down to this line. Okay, so for our specific function, it ends up looking like this. If the length of x does not equal the length of y, then stop. Vectors are of different lengths. Otherwise, you're just going to do the same bits that we had before. Okay, and now that stops our it stops the evaluation of the function when they're not the same, and so we don't end up with that recycling problem. We could also, however, make the error message more meaningful. And this is something that becomes very important when you are writing your own packages. So some of you might go on from this class to write your own R packages, and some of them might be used by a fair number of people. That might be people in your lab, it might be people in the general public, it might be people in a very small sect in your field, whatever, okay? But if more than basically just you are using it, then you want to have meaningful error messages. And actually, I would argue, even if it's just you, you probably still want to make the error messages as meaningful as possible, because future you may not remember how you wrote the code at this present date. And in fact, that happens all the time, right? So one way we could make this error message more meaningful is to state the lengths of each of them, okay? So I could do that like this, where in this case, I'm first checking the lengths. If they're not equal, then I'm creating an object which I'm calling v-lengths, okay? And I'm just pasting together x equals, and the length of x, and then comma y equals, and then the length of y. And then I'm saying stop, vectors are of different lengths, v-lengths. And then you can see error, vectors are of different lengths, x equals 7, y equals, it would say 14. Okay, yes.
So, question that I have on error messaging, specificity, because there are situations where vectors of different lengths would work if they were divisible.
Yes.
So this error message isn't like how much of like the information around the function of the message.
Yes. So yeah, so to repeat for Zoom, the question is how much of the error message specificity should you go into, basically, right? And this is, I would say, sort of more the art versus the science of this. It's similar to like when you're in data viz, right? When we were talking about access titles, like you want to say what the thing is, and you want to say the units that the thing is in if it's measured, right? But you don't want to go overboard. Like you don't want to say time AD, right? Like but you do want to say like time in years or whatever that is. So this is a similar sort of thing. This might actually be going overboard just a little bit, but it still could be helpful. The other thing is though, this the way that we've written this function so far, it will stop if they're not the same length, period, right? It won't do any recycling. So we're actually going to continue to push on this more, and we're going to change it so it will work if it's recyclable, and it'll do something different. Okay, cleaning this up just a bit more, I've changed the v lengths here a little bit, so it now has, it'll come out on a new line, basically. these lengths, so that looks a little nicer, I think. But the other thing I did is I added this call dot equals false. So when I go back here, notice how it says error in both NA, A, C, B, B. All of this part, that's the call, right? So it's just echoing the call that you had and then printing the error message. You might want to do that. That's the default. Very often I find it's not helpful and it just makes for longer error messages. So instead, you just put call dot equals false, and then the error looks like this, right? Error vectors are of different lengths, x equals 7, y equals 14, okay? So that's like super minor, but good still. Okay, I also mentioned if you just want a quick error message, you can use stop if not. This is often useful when you're debugging or when you're writing a function that's just quick, that's just for you in this one script. And so you're just saying stop if not, and then you put some condition in there. So for example, stop if not is dot numeric x, and then it will print this error if x is not numeric, right? And it just says is dot numeric x is not true. Okay, so it's not the best error messaging, and that's why you should probably prefer stop to stop if not, but it can be a nice quick way to write an error message, error condition. Okay, questions so far? Okay, so we're going to kind of shift a little bit, and we're going to talk about warnings now. Okay, so errors will actually stop the evaluation of the function, and it will error out with some message, right? Warnings are different. Warnings will warn the person who ran the function about something, but it will continue to carry on with the function. Okay, so it will not stop the evaluation of a function. Why is this all of a sudden stop working? Okay, so what we could do in our case with this function then is we could build in a warning that said if the vectors were recycled, an error if they're not recyclable and they're different lengths, and otherwise continue on. Okay, so basically it's going to check if they're the same length. If they are, great, we continue on. If they're not, then check if they're recyclable. If they are, then you can continue on with a warning. If they're not, then you error out. Okay, so it's like this kind of tree of decisions through this function. Okay, so one way to do this recyclable thing, is to use what's called the modulo operator. Okay, this is a common thing within all programming languages, I think, or most of them anyway. In R, it is designated by this %%, okay? And that's to stand in for basically divide. And what the modulo operator does is it tells you the remainder of a division problem, okay? So 8, this thing, modulo, 2 returns 0, right? As does 8, 4, because there is no remainder in those, right? 8 divided by 2 is 4, 8 divided by 4 is 2, there's no remainder, right? But if I do 7, 2, I get 1, right? Because it's, 6 would be, right? And similarly, 7, 4 is going to return 3, okay? So basically, we can use the modulo operator to see if it's divisible, because it should return 0. And if it returns anything other than 0, then when we're dividing by 2, right? If it returns anything other than 0, then it's not recyclable. Okay? So this is now one approach that we could use. We start out right at the beginning and we check the lengths. Okay? And then if they're not equal, we come into here, we say the length of x, we say the length of y. So now we have objects for those lengths. We paste our v length thing together. Okay? And then I'm saying if the length of x divided by the length of y equals 0, okay, but that divided by is actually checking for the remainder, or the length of y divided by the length of x equals 0, then, so if either of those conditions are true, right, a divided by b or b divided by a, if either one of those have no remainder, then we say warning, vectors were recycled, and then we state the b lengths. Otherwise, we're going to stop and return that error message. Okay, and again, notice these brackets here to here. So if these lengths are equal, all of that stuff in this function only happens if those lengths are not equal. If they are equal, all of this gets skipped. Okay, and we just jump straight to this final line. All right, so we can test it out now. Both in A, B, B, we get a warning. Vectors were recycled. We can do it again here, but I'm removing the first element in that second vector. And so now they're of different lengths and we get an error. Okay? Does that make sense? So, yeah, go ahead.
Could you do the warning message and still return it?
Yeah, so that is what happens. So notice it says warning, but then you get the 4 there too. So that's the difference between a warning and an error, is a warning will continue on with the evaluation of the function. So if we go back here, if we get to this point, it will throw that warning, but then it won't evaluate this part because this is in the else part, okay? And this really should probably be up here. I don't know why it's down there. Like usually it's if, and then your ending parenthesis and then else on the same line. So this should be up there, but somehow it got down. So it will throw this, but it will not evaluate this, and then it will continue on and it will evaluate that. Okay? All right. Okay, questions on that? Okay. There's also a concept called refactoring, okay? What refactoring means is that you're changing the internals of a function, but the output is not changing, okay? The output of a function does not change with refactoring, but the internals do. And there's numerous reasons that you might want to do this, okay? One, which is the primary reason we're going to do it here, is for code readability, okay? Another reason, which is another reason we're doing it here, going to be doing it here, is for debugging, okay? If you have one function that's this long, it's going to be very difficult to debug, okay? If instead you have 7 functions that all work up to one singular function that's 5 lines long, and then it calls all of those other 6 functions, that's going to be much easier to debug, because if there's an error, it's going to go through that tree of different functions, and you'll know which function that the error occurred in, and if each one is less than 10 lines, then you'll know it's somewhere within those 10 lines. Okay, so that's the other reason. There's also, and this is not why we're doing it here, and I would say 99% of the time this is not why I refactor, but you can also refactor for performance reasons. Okay, so maybe you have written a function and it works and it does what you're expecting, but it takes 5 minutes to evaluate every time you run it. Okay, you might be able to refactor it and figure out some optimization gains somewhere inside of the function. So the output of the function is exactly the same, but now it takes 20 seconds instead of 5 minutes. Okay, that's another reason that we refactor. Okay, all right. So all of this is a lot, and most of this is not really like the biggest deal, right? So if you are feeling like a little freaked out by all of this, that's okay. What we started with on this lecture last time is much more important than this stuff, but we're going to continue on with it for a little bit. Okay, so this is just reiterating what I just said. Okay, actually we're going to get to the refactoring for the next lecture, I think. so the one we're going to start here in a minute. Okay, so return values, quick. Got, 9 more slides. By default, a function will always return the last thing that is evaluated. Okay, and you can override that behavior by using the return function inside of a function. Okay, I believe it's best to not use the return argument, the return function, inside a function unless you are returning early. Okay, so for example, real quick pop quiz. Look at this and just think in your mind, what is this going to return? So let's say I said add 2 and I said 3. What would my result be? Okay. Okay, 5. No, you get actually nothing. Okay. Because it is stored in result. Okay. Interestingly, though, it actually is there. It just doesn't print. Okay. So if you were to run this and store it into something else and then print that, then it would work. But this is confusing behavior. And you probably want to omit this part of it that I have highlighted here. Okay. So alternatively, you can do it like this, result, result, or you can just not assign it to anything at all and get that. Or thirdly, you could say return result. Okay. So this last one is what I'm advocating that you should not do. Okay. It's not like the biggest deal, right? It's not like the biggest thing in the world. It's more a stylistic thing. But I think it's preferable because then when you see return within a function, you generally know that's because there's something that is making you early exit out of the function. Okay. So when to use return? All right. Well, I've already mentioned that. You do it when you're early return. Okay. Another thing to think about carefully when you're writing functions is the actual name of the function that you're writing. Okay. It's very easy and very enticing sometimes to write functions that are called like f, right? Because it's just quick and easy and you just want to get it written and get it over with. The problem is if you come back later, you're like, even a couple weeks later, you're not going to have any idea what f is or what it does. And you're going to have to go through all of the code to figure out what it's doing. Okay. Better in this case would be to call it something like p-tile. Okay. Because that's what this is doing. It's creating it's taking any numeric vector and it's returning the percentiles for that vector. Okay. But even better would be percentile underscore df, because now you're getting an idea of what it's doing, computing percentiles, right? And what the output is going to be, a data frame. Okay. So when you're writing functions, try to be careful about what you're naming them and try to give them as meaningful of names as you possibly can. This turns out to be much more difficult than you would expect. And I very regularly screw things up when I'm starting. So like I might have something that's like df underscore percentile and then later have something that's like something underscore df, and then I need to like realize that I'm inconsistent with those and then flip them and then make them consistent, etc. So this is a much harder problem than this appears. This is an easy example, right? So I don't really have a lot of advice for you on how to name them. I do think including something on the return value is nice, but it's not necessary all the time. And sometimes it can just muddle things up. And it's maybe not the best when if every single function you write returns a data frame, then appending it with underscore df is probably not super helpful, right? But if some of them return vectors and others return lists and others return data frames or whatever, then that might be helpful. Okay, the other thing you can do is actually use the output of the function to help it be more interpretable. Okay, this is a little bit tricky, and I'll show you a different way to do this here in a little bit too. That's also not any less complicated. In fact, it's probably more complicated. But in this case, I'm creating this thing called arg, okay? And I'm saying match.call, which is just going to match the call that is given. So whatever is given to the function, it's going to match that. And then I'm taking that information and I'm transforming it into a list, okay? Then, so this thing is called arg, right? Then I'm saying as.character on argx, because x will be an element of that vector, because that's what this thing is called. And I'm going to collapse it with this. So that's what the name, the first name of D is going to be. And that ends up being nice because you can do things like this, okay? Random vector, rnorm 100. And then when I say percentile df random vector, whatever I feed it here becomes the name of it here, okay? And so when I have things like this, rnorm 50, it becomes rnorm underscore 50, okay? So that's kind of a neat little trick that you can use to help actually make the output of your functions more meaningful as well. All right, we're gonna just skip that. Okay, the last thing basically for these slides, this is the last thing for these slides, is thinking about dependencies. Okay, I've kind of talked about this a little bit in the past. Dependencies mean that your function depends on other code, other people's code, right? So for example, let's say I write a function that creates a plot and I use ggplot to create that plot, okay? That means that function depends on ggplot, okay? Dependencies are something to think about for sure, but they have like they're a bit of a double-edged sword, right? So if you have a ton of dependencies, that's going to be difficult to maintain because as those other packages become updated and they change, it may end up resulting in your code no longer working. And so you're going to have to go and modify your own code, not because of anything that you did, but because your packages that your functions depend on changed, okay? I will say, if you're using tidyverse code, or really most of the RStudio code, that's unlikely to happen, okay? They are very, very, very careful about writing code that will not break things for you, okay? So if you are using tidyverse code, then it might advance more down this line. But if they're going to introduce breaking changes, then there will be big warnings about it, and they will usually soft deprecate it, so it will still work for a long time before they fully deprecate it. Okay, and in other situations, like gather and spread is a good example. Those became pivot longer and pivot wider, right? But gather and spread are still supported. They still work, and they will work forever. Okay, so my approach, however, because I've been bitten by dependencies in the past, is to worry about it a little bit. Okay, so even if it's tidyverse, I personally prefer to try to write my code with fewer dependencies. I'm not like super like hyper about it, right? If I have some dependencies, that's fine, but it is something to consider. Okay. So these slides have some other things to consider as you're thinking about it. If you're writing a function and it's just in your script, right? Even if it's just in your script, you might want to consider namespacing. So saying the name of the package, : the name of the function within your functions, because that'll make it very clear that this function depends on this other function from this other library. Okay. All right. Okay. So that's it for those slides. Any questions on that before I switch over? Yep.
I have a question about return value. What if you want to return more than one value?
Then you have to return a list, basically, that has those multiple values. So yeah, so the question is, what if you want to return more than one value? Inside a function, you can only return one thing. So you either have to return it as like a data frame or as a list that has but this is why lists are such a common return value from functions, because lists are super flexible, right? You could return 70 different things, all of different types and dimensions and whatever in a list. But I will also say lists are more difficult to work with, right? So if you have a function that is returning a bunch of things and they're in a list, then there's a couple of different things you could do. You could either write higher level functions that call that function and then just pull the thing out of the list that you want, or you could have arguments within your function that specify what you want to return rather than returning everything all at once. That make sense?
Yeah, but like, can we return, say, two things with the return statement? Return A, comma, B.
You can as a vector or as a list, but like you can only return one thing. So if there's A and B that you want to both return, generally you're going to wrap them in a list and return A and B in a list, in a single list.
Is return a function?
Yes.
Okay. Function on parameters.
Yep. It's just the thing that you want to return. And again, like you don't have to use return unless you're exiting out of the function early. Okay. So I think we'll see an example of that today.
Second question is about dependencies. I mean, I've seen that, if you depend on a package, you kind of store a local version of that package so that your function always works.
Yeah. So to repeat or zoom with dependencies, there are ways to store a local version of the package for you. That's absolutely correct. The best way to do that is with a package called renv or env, our environment. And that is a great way to manage package dependencies when you're doing something like, say, writing a paper, right? And you want to write a script for the paper and you want to make sure that 20 years from now, that script is still going to run. Renv is going to be your best friend, right? That's going to work great for that, because what it's going to do is it's going to create a lock file, which has every single package that your script depends on and the specific versions of them. And then when you run renv restore, it's going to go out and get those specific versions of all of those packages, and then it should run after that. However, that's a great way to manage dependencies for something like a paper. If you're doing something like an R package that is going to be out there and used by other people, that's not going to work. Okay. So if you're doing something beyond just something that you're going to keep locally, then dependencies are just something that you have to live with. And there's a good reason, like when packages are being updated, they're not just being updated just because, right? They're almost always being updated for good reasons. Sometimes it's new features, sometimes it's performance gains, but often too, it can be things like security problems, right? This is more common in like web stuff than it is in R stuff, but it is still a concern. And so you want to update those packages as they're coming in, unless you have a really good reason not to. And so something like a script for a singular paper is a good example of something that you kind of want to just like freeze in this state and just like kind of set it aside and say, this is how it's going to be for here. That help?
Yeah. Like how about a website or like an interactive?
No,
No?
don't want to do that there. No. If you have a website, you for sure don't want to have packages like frozen, because everything is changing on the web all the time. And specifically with security problems, things get out of date and then you have security vulnerabilities and people can get in and steal all your data.
Okay.
So, yeah. Okay, any other questions? Okay. All right, so the agenda for the rest of today, we're going to talk about what makes a function good, okay, versus bad. We're going to also talk about building up functions, so starting from something and then building up from there. And then we will talk about non-standard evaluation. Non-standard evaluation is a very difficult topic. It's not one that I'm expecting any of you to be fluent on by the end of the day. It's not something I am fluent on, and I've worked with it a bunch. whenever I have to use non-standard evaluation beyond the very easy stuff, I have to do trial and error until I get the thing to work, right? That's just how it is. But I would not even be introducing the concept of non-standard evaluation were it not for the tidyverse. But non-standard evaluation is used prolifically throughout the tidyverse, which is great for interactive use, but makes programming with it more difficult. So that's why we will talk about it. We're just going to touch on it. I mean, we'll talk about it for a while, but we're just going to still touch the surface of it. Okay. So learning objectives, understand how functions build on top of each other. This is another thing I've mentioned a couple of times, but that I think is incredibly important is that you should always be aiming to write small functions. Okay. So a general rule of thumb is, and I don't always follow this myself, but like if you are looking on your laptop screen, not like some giant screen, but just your laptop screen, your function should be able to be maintained within that screen. If you're having to scroll like a lot to see the entire body of your function, that's a good indication you should probably break it up into multiple functions. Okay. The other thing is that your function should do one thing. Okay. So it should do one thing and do it well. That doesn't mean that it can't have a bunch of additional arguments, but within that, that function is probably going to be calling a bunch of other functions that are all doing one thing. Okay. And then understand non-standard evaluation, what it is, even if it's not something you feel super comfortable with. Okay. All right. 2 minutes. If you are on Zoom, you can just think on your own and maybe jot a few things down on paper. Locally here, the four of you can chat. What do you think makes a function good or bad? 2 minutes. Okay, somebody from Zoom, tell me, what do you think makes a function good or bad? You can choose whichever one you want to do.
A characteristic that makes it good is that it works and does what it's supposed to do.
Perfect. Manuel said a characteristic that makes it good is that it does what it's supposed to do, right? That is a great answer. All right, somebody else on Zoom, tell me something that makes it bad. What would be something bad that a function would do, or about a function?
It's really complicated or has multiple functions nested in it.
So the first part, yes. The second part, no. Having multiple functions nested in it is actually good practice, and so we'll show this more. But the first part, yes, it could be super or overly complicated. So there could be an approach to do it to solve the problem that is complicated but works, and then another one that's just like super convoluted, taking you all over the place, and it's really hard to track what's going on. So that is a good example of a not great characteristic of a function, and that would be something we would want to refactor to make clearer. Okay, somebody in person, tell me something that makes a function good.
It has warnings and errors.
Good. It has warnings and error messages when they're needed, right? Stop. Oh shoot. It actually stops when it should stop, and it provides useful warning messages when it's getting unexpected inputs or whatever. All right, and then somebody in person, tell me what makes a function bad, something that makes a function bad.
If you don't know what type or style of data you're going to get as an output.
Good. So you don't know what you're going to get as an output, basically. So sometimes it's a string, sometimes it's numeric, sometimes it's an atomic vector, sometimes it's a list, sometimes it's a matrix, right? So it's unexpected. The output is unexpected. sapply is a good example of that. Okay. This is from Hadley's Master R training. This is from years ago. I attended his workshop, and I really liked these slides of his, so I just took them and put them in my slides with reference, obviously. So there are sort of these tensions that exist in R. And some of them are different than in other programming languages. And so I think they're worth thinking about. So the first one is this sort of land between pure sort of programming all the time and interactive exploration. And R tends to be sort of more down here. R was by design meant to work with data, and so therefore it's meant for a lot of interactive exploration. However, it's also powerful enough that you can build programs with it very easily, right? But base R as a whole is sort of leans more closer towards the interactive exploration end of things, okay? There's also this ideal between being very conservative as a programming language as a whole or very utopian, okay? So utopian would be like, we're going to use the latest and greatest things and we're going to make this as good as it can possibly be all the time, right? And the problem with that is it's going to change a lot. It's going to change very rapidly. And so all of those dependency problems I talked about a little bit ago, those are going to be quite severe in a very utopian sort of world. R, base R, tends to be highly conservative, okay? And this is a great characteristic for certain reasons, like if you wrote code in 2005 from R using only base R code, it would probably still work today, which is pretty amazing, right? And that is how base R has a very strong preference for that. But the tidyverse is not that way. The tidyverse is much closer to the utopian side of things. So that's one of the tensions that exists sort of just within the R ecosystem and is worth being aware of. Okay, so I say that this first part mostly to get you to think about when you're creating a function, where are you on this list? Is it pure programming? Is it meant for interactive exploration? And are you building something that you're going to be fairly conservative with? In that case, you're probably going to only use base R functions. Or are you more towards the utopian side and you'll use all the most modern functions that exist? Okay, but with that, knowing that you'll have potentially dependency issues. Okay, when we're writing functions, we have this sort of cascade of functions usually that we go through. Okay, so when you call one function, you're actually not just calling that function. You're calling that function, which calls a different function, which calls another function, which calls another function until you get to the end. Okay, so the worst is this first line, right? You start out with some bad input, which happens, right? And it goes through all of this lines of your function, goes through multiple different function calls until it gets to this point, and then it can't go on anymore. And so you get some super obscure, weird, uninformative error. And it's uninformative because it's an error for this function down here, which may have very little to do with this function up here. Okay, it might just be doing some specific thing that is going to then go back to the other function and continue on, right? But that error message is very likely to be uninformative. So that's not good. Much better is once there's bad input, immediately error out and provide a useful error message. So that's kind of what we were working on before with our previous function when we were erroring out when we had a vectors that were not the same length, okay? And they were not recyclable. This is another just sort of continuum. So the best that a function can do is give you the right answer, right? If that's not the case, if it can't give you the right answer, then the next best is to provide a useful error message. So it didn't give you the right answer, but you know why, and you can go and fix whatever you need to fix so that you can rerun the function and get the right answer. Less helpful than that is a not useful error, and I know we've all encountered that a lot, right? And then the worst is there's no error message, there's no anything, and you get an answer, and so you continue on, but that answer is actually not correct, right? And unfortunately, in R, because it's an open source programming language, this is true of all open source programming languages, it's very likely that you can come across a package on GitHub or somewhere that is maintained by one person and they can't do everything. And so they end up with this sort of thing where you get an answer, that actual answer is not correct. Okay. So again, when you're writing your functions, obviously you want to try to have the right answer, but barring that, you really want to try to make sure that you have useful error messages, if not. Okay. So operationally, your functions, when you're writing functions, should do one thing and do it well. Be careful about naming functions. We've talked about this just a minute ago. And then embed error messages and warnings that are useful and helpful for you and for the user to do. Okay. The other thing that I would really encourage is to refactor your code. Okay. I think of writing functions that are going to be maintained. Okay. There's like a very clear distinction here in my mind between writing a function that's a one-off for one script and that you're going to use it one time and continue on versus writing code in more of like a production environment where you're going to be actually needing to maintain it over time and other people are going to be using it and interacting with it. So what I'm talking about now is more that latter case, okay? But it is totally fine and acceptable to write really messy code to start, okay? It's just like writing a paper, right? You write a paper and your first draft is maybe all over the place and you have text in the wrong place and you have your arguments don't quite make sense, but at least you got something on paper and that's like 80% of the battle, right? And then you go and revise your paper and you go through more and more drafts and by the end you get something that's pretty polished and you feel pretty good about it. That's what refactoring is. Okay, it's that same process. You write an initial function, it does what you think it's going to do, that's great. Then you refactor it to make it better, to make it easier to read, to make it make better error messages, to make better warning messages, etc., or even to have any warning and error messages. Yep.
So let's say they were writing a function that's using other functions, and we had some sort of bad input, and one of those functions that we're calling is getting back at that. Are you able to do anything with that error message in the function? Like, can you say, oh, I know that this error message is this with there?
Yes. Yes, there are ways to do that. They are not particularly straightforward. However, purrr does make them easier. So remember when we were looking at purrr safely, and you could run it and you'd get the list back that has the result and the error. There's another one that's called purrr quietly. I think that's right, where it will return the result if it's there, but it will also return a warning, an error, and a message. And so you could write a function that is calling safely or quietly on that function that would return whatever it is, either the error or the message or whatever. And then you could use that to then provide some other message if you needed to. Okay, so going back to this is the function that we kind of ended with in the last lecture. So I'm going to give you just like a minute here. Just look at this and try to think of at least one way you think that this function could be cleaned up, how this function could be improved, refactored, at least one way. Okay, maybe 30 seconds is okay. What do you think? Any ideas? I will admit freely, this is a difficult process, especially when it's not your function and you're just looking at somebody else's function. But does anybody have ideas of things you might possibly do to refactor this code to make it better in some way?
Just a good place to start is like to not, so there's already a redundancy with length X being called in the first if statement. So if you defined LX and LY
Yep.
above the if statement, then you could pass it and not have to have length X and length Y written out multiple times.
Good. So we have length X here, and we have length X here. We have length Y here. We have length Y here. So we could go ahead and just move this part up above the if, and then we could just say if LX not equal to LY, right? Instead. So that's one thing. Any other ideas? Yep.
You could do a similar thing to pull your kind of recyclability
Mm-hmm.
calculations, also pull those to the top,
Yep.
and then you can call back to that when you're programming your warning messages.
Yep. So what? So basically, we could take this, and this would be essentially a test that we could run at the start. That would be, we could call it recyclable or whatever, and then it would have that, right? And then we could continue on with that. Good. Any other thoughts? Okay. Oh. Okay, the way I decided to do this is to do similarly to what you said, calculate if they're recyclable. However, I did it slightly differently. Instead of running that test inside the function, I actually pulled it all out and made it its own function. Okay, this is what I would say is the most common and approach to refactoring, is just pulling stuff out and making it its own function. Okay. That way, we can just call that function within our function instead of writing all the logic of that test in our function. Okay, so I could have the LXLY here too if I wanted to, so I could refactor this function more too if I wanted to. But I just have length X, length Y, length X, test 1, test 2. If any of these equals 0, then it's going to return true. Otherwise, it's going to return false. Okay. And then we can test first that the recyclable function works, right? So is A and B recyclable where they're the same lengths? So yes. Is A and BB recyclable? Yes. Is A and BBB? Yes. What about AA and BBB? No. Okay, so this is very quick testing, but it's evidence that our function is working the way that we expect it to. And now we can use that function within our function. This is still actually, it kind of made our function more complicated looking though, right? Because now it's saying if not recyclable, then we're going to stop, right? If the lengths are equal, then we're just going to return. So here's an example of an early return, right? So this is, they're equal. And then otherwise, if they're recyclable, then we're going to do a warning. Okay, this could be cleaned up in a couple of different ways. This is probably not the best way to use that recyclable function, but it does still have to be something like this, where you're saying if recyclable, if not recyclable, and then whatever, right? And the reason I ended up writing it like this is because I wanted, if the lengths are equal, right, then I don't want it to return that warning. And so that's why I'm returning the thing here. Whereas here, we saw before, if they're the exact same length, recyclable is still going to return true, which would mean this warning would still be thrown, right? And then this would happen. So that kind of helped, but it actually kind of made it worse too, right? So what can we do instead? Well, first we can test it to make sure it's still working. Because again, remember with refactoring, the idea is the output does not change, only the internals of it change. And the internals of it change to make it either more readable, more efficient, or reduce dependencies or whatever, something like that. Okay, so that works. This also works, AB and BBB. And then this one also works. Or no, this one does not work. Vectors are of different lengths and not recyclable, 14 and 21. And then this one, they are recyclable, so we get the actual output, but we get that warning as well. Okay, so what else could we do? In this case, we can actually make the errors and the warnings a function, okay? And that will help us a lot, okay? So this function could still probably be cleaned up more. We could probably still refactor it if we wanted to, but it's pretty straightforward, really. It just looks longer than it actually is. So we're first checking if the lengths are equal, and notice that bracket there goes all the way down to here. So if the lengths are equal, they're not equal, right? If the lengths are equal, then nothing else gets evaluated. Okay, this is only if they're not equal. Then we say if it's recyclable, throw this warning, else throw a stop message. Okay? And now our both NA function looks like this. Check lengths, xy, and then sum. Okay? And so you can see when I'm looking at this function, it's much more clear what's going on. We're first going to check the lengths of x and y. And it's not super clear what that means, but we get an idea that we're checking the lengths, right? And then we're going to continue on. And if we wanted to know more about the check lengths, then we could go to that function and look at it. Okay? And because that check lengths will throw a warning or an error, this function will not continue if the error is thrown. So this part doesn't get evaluated if check lengths throws an error. Okay? So we can test it both in AB, ABB, we get the warning, and AB, BBB, we get the error. And so all of this looks exactly the same, right? Which again, it's supposed to. That's the idea. Okay? So why would we do this? In this case, it results in, I would argue, much more readable code, right? The final function that we ended up with is much more readable, and we still have all of the same behavior with the warnings and the errors. The other thing is the recyclable function in particular is very possibly helpful for us for other functions. Okay, so it's very likely that we could use that function in other functions besides our both NA function. Okay. And then the last thing, and then check lengths might also be useful, but it's a little less likely than recyclable. But the last thing is it also really helps makes debugging easier. Okay, so I've mentioned this a couple of times, but I'm going to show you an example here. Okay, here is an example where we have a whole bunch of different functions. So we have f, which takes an argument a. F calls one function called g. Okay, g calls h, h calls I, and I is this function that says if not numeric, stop d must be numeric. And then I says d plus 10. Okay? Now, if I say f of a, then I'll get the error that, I'll get this error here, which may or may not be helpful. In this case, it is pretty helpful, but we could pretend that it's not, right? But we can then use this function called traceback. Okay? Traceback is a very useful function when you get to debugging complex functions. And what it's going to do is it's going to return the call stack. Okay, so it's going to say, you called f of a in the first, this is a screenshot. So you called f of a in the first part, right? That called g of a, which called h of b, which called I of c, and then we got this error message. So we know this error occurred in I. Okay, this is a super simple example, and so it's pretty clear what's going on. But we would know at that point that we need to go to the I function and figure out what's going on there. Okay, and that I function is maybe like 7 lines of code versus if you had all the logic for all of those functions all in one singular function, then it's going to be really difficult because it's like the error occurred somewhere in these 150 lines of code, right? And that's much more difficult to track down. All right. So that's the other reason. And this is exactly what I mean when I say your function should do one thing. Okay, so it shouldn't be doing a ton of different operations to get to this one output. It should be doing one thing. And then it can call a bunch of other functions, but the actual operations that are occurring within your function should be one, basically. Okay? Does that make sense? So then you're going to write functions so they sort of layer on top of each other. All right. how about we take a break before we start this? That sound good? All right, let's see, what time is it? 2:06. I don't know. I'll just set a timer for like 7 minutes. Does that sound good? Ish. All right. Okay. Onward. So, as I mentioned, non-standard evaluation, this is a high level look. This is a very advanced topic that I am not super expert on. You'd probably have to have a CS degree to be like amazing at it, or just spend a bunch of time on it. So this is the purpose of this is not to dive that deep into it. It's to give you an idea of what it is and why you will need it and how to use it. Okay. So I sort of mentioned this earlier, but were it not for the tidyverse, this would not be a topic in this class. I don't think it's generally that important of a topic. However, because of the tidyverse, we sort of have to talk about it if you're going to be writing functions using the tidyverse, because non-standard evaluation is used everywhere in the tidyverse. Okay, so non-standard evaluation is an implementation of different scoping rules. So we talked about scoping a little bit last class or the class before that. Can't remember which. But basically, scoping is, right, if you have a function, it's going to look for the thing, like let's say you have something that you're calling data, right? It's going to look inside the body of the function for something called data. If it can't find it there, it's going to look to the global environment and see if it can find it there. If you have a function that is inside of a package, it will first look inside of the package, or it will first look inside the function, and then it will look within the namespace, which is the package itself. So all of the other code in the package. Okay, and then it can go a lot further than that, but that's like the basics of lexical scoping, which is what's implemented in R. Okay, non-standard evaluation sort of changes those rules, and it says, okay, well, that's how it happens usually, but we're going to do this more manually. We're going to say, here's a thing, and we want you to evaluate it here, okay, rather than the typical rules. Okay, so for example, in dplyr, when you specify something, like let's say you're using select and you say select MPG, non-standard evaluation works by quoting that MPG thing and then evaluating it within the data frame rather than looking within the body of the function for something called MPG and then looking at into the thing. Okay, so again, this is just reiterating what I just said. It captures an expression, which is called quoting, and then it uses that expression or evaluates it within the correct context. So if we say select X, right, it's going to look in dfx, it's going to look for X inside the data frame rather than looking for X in the global environment, for example. Okay, so it changes sort of the lookup, how it's going to look for specific things. So this is, we're going to start out with some base examples. This is that same function I showed you at the start of class. Okay, so we have, we're going to basically sort X, and then we're going to create a data frame that has that sorted thing. And then we're going to compute the percentile for those sorted things, okay, using this ECDF function. Then we want to change the name of that to this, okay? What we can do with base R is use something called substitute, okay? And what substitute does is exactly what it sounds like. It's going to take the input and it's going to substitute it in there. So when I say substitute X, what I'm going to get here is whatever is fed to X. I'm not going to get actual X, okay? So when I say rnorm 105.2, it's giving me back here rnorm 105.2, okay? And we're getting underscores between them because I have it paste 0 with the collapse as an underscore, okay? that kind of make sense? What's going on there? So confusingly though, substitute, this is base R, right? Substitute operates just like quote. It quotes the input if you're using it outside of a function. So substitute works differently depending on whether you're using it inside a function or outside a function. Okay, so if you're using it inside a function, it does exactly what we just saw. Takes the input and substitutes in whatever the input is. If you're using it outside of a function, it's just going to quote that input that you give it. Okay, so here's an example. We say quote, and then we have some R code, right? Subset df select equals var. Quote returns that, right? It just quotes the thing that you gave it. It could be anything, any R code. It doesn't even have to be R code. It could just be like whatever. Whatever it is, it's just going to quote that. Substitute does the exact same thing if it's outside of a function. But when it's inside of a function, it does something different. When it's inside of a function, then it actually returns. Okay, so here I'm creating a function called extract var, and I say function df var, and then I'm saying substitute df. So in this case, that var argument actually isn't even used in the function yet. Okay, but when I run this, when I say extract var empty cars, what I get back now is empty cars instead of substitute df or whatever. Make sense? All right, good, because we're just warming up. All right. Now, to get it to actually work, we have now quoted it. To get it to actually work, we need to also evaluate it, okay? And we have to evaluate it where we want to evaluate it, okay? We can't just say substitute eval, whatever. We have to do it in the specific context that we want. So here, I'm using subset, and I'm saying substitute whatever the df is given and evaluate it right there. So in this case, I am saying I'm basically quoting and evaluating in the same spot, but that's within this subset function, which requires a data frame as its first argument. Okay, so now I can say extract vars empty cars. Notice I'm giving it empty cars as a data set, but like I'm not having to do any quoting here or whatever. Okay, and that gives me back this, which looks good. So why eval? I've mentioned this already, but substitute is quoting the input, eval is evaluating it. Okay, so this is difficult to wrap your head around, but it happens all the time in the tidyverse. And specifically, notice how I'm still wrapping this in a string. Okay, in the tidyverse, you don't have to do that, right? You just pass the bare thing, the bare symbol for whatever it is, and it knows that that symbol should be evaluated inside of the data frame object and not in the global environment. That is the only way that they can make that happen. And that's one of the reasons that the tidyverse is so different from base R, because base R, you don't really ever do that. You don't really ever pass a bare name of anything other than maybe a data frame or an object, more generally, to something and expect it to work, right? So in the tidyverse, this is implemented so frequently, so much, that they have actually developed their own library and their own system of non-standard evaluation, which is called tidyeval, okay? And that is all implemented through the rlang package. All right, continuing on with this example though, we can actually continue this even more. So I can say substitute the var this time, okay, instead of the df, and then tell it to evaluate it inside the environment of the data frame, okay? And now we have empty cars MPG. Notice I don't have to put quotes around MPG anymore, and it works because it's quoting that MPG. So it's not actually evaluating it until I tell it to. And once I tell it to evaluate, it's only doing it inside the data frame context, okay? So this is the equivalent of df $var. Okay, it's the exact same thing. However, this function is more useful than that one because you can use it programmatically. So you could programmatically swap out the data frame or the variables, and it would work just fine. That is not the case with the $, right? All right, so that's that. Okay, you can also do this other ways, right? So this is another way that I can sort of force it to be evaluated within the data frame environment. Here I'm saying df, comma, so all rows, and then I'm forcing this to be a character. So I'm saying as.character substitute var. I have to do as.character because otherwise, when I do that substitute, what is actually being returned there is a symbol, okay, an R symbol. So that is not the same as a character. And so by doing this, it's the same thing as the previous slide where I am forcing it to evaluate inside the data frame environment. It's just two different ways of doing the same thing. Okay, we could also add additional arguments like drop equals false or whatever, and that would work. Taking this even further, maybe we want to say, well, you could do one column or n columns, right? And so to do that, we would just pass the dots. So here in the actual arguments of the function, I have the data frame. I'm going to pass the dots. And then down here, I'm going to substitute the dots, okay? Which means all of them. But to get that to work, I have to wrap it in this thing called an A list. It's just like a list. It's just basically inside a function, okay? And so this is like, I can't remember what it is. It's like alphanumeric list or something like that. I'll look it up in a second, okay? But then we can do that same code that we had before. But notice I'm saying -1 here. That's because the first argument in this as.character vector is actually going to be a list. Okay, so we drop that. The rest of the variables are there as characters. And now we've essentially replicated dplyr select. Okay, you can use extract vars, empty cars, mpg, sil, disp, just, and it's they're all just bare symbols. We're not having to use quotes, and we have essentially replicated dplyr select. Okay, questions? Yes.
I had a question on the previous slide, actually.
This one.
Yes. Or it meant that where you were saying that it's, yeah, where you can't swap the program.
Yeah.
Why is that? Just switch out the data.
So what I mean by that is, let's say you wanted to loop through a list of data frames and loop through a list of variables. You couldn't do that with a $sign. So you'd have a $sign where the data frame is being swapped out and the variables are being swapped out at the same time. But you could, in this case, where you have two different arguments that you're passing it, and you can interactively swap them out.
What about the like numerically indexing them?
Yeah, so you could do that with brackets instead. And actually, I would not use indexes. I would use quotes, and I would use the variable name. So like sort of just a general rule of thumb, it's best to avoid indexes whenever you can, because column orders can change. And so using the column names are going to be safer than locations. Other questions? Anybody on Zoom?
What happens if you do substitute, like, without that, do you have it for an error, does it not work?
Yeah, it just won't work. Yeah, because what's going to happen is so you could get this to work 100% with standard evaluation if you use quotes, right? But this MPG right here, passing it as a bare symbol like that without quotes, the only way you can do that is with non-standard evaluation. That's really the main thing here. And so You could, if you did this without substitute and without, like if you did exactly this without substitute, it would work perfectly, except you would have to pass this as a string still. Otherwise, you would get an error because it would be looking for an object called MPG, which doesn't exist inside the function and doesn't exist inside your global environment. Or if it does, it's probably not what you're expecting it to be. Other questions?
Why is empty cards not in like code?
Because it is an object. It's so that's a good question. Why is empty cars a bare frame? Empty cars is a data frame, which is an object, right? So you can always pass objects to things, but MPG is not an object, right? It's a column name. And so you'd have to usually pass that as quotes, but you don't in this case because, and that's exactly why substitute is needed, is to quote it and then evaluate it in the correct spot. Otherwise, it's going to be looking for an object called MPG that is in your function or in your workspace. Good clarifications. Anything else? Okay, so why is like a big question here, right? Why is non-standard evaluation used so frequently in the tidyverse? And why don't we just use quotes? The main reason is because it makes interactive work much easier, okay? So if you're never having to worry about quotes, you can feed it quotes and it will still work. So you can give it bare symbols or quotes, and like for manufacturer, model, and highway, either way, it's going to work. And so it makes interactive work much, much easier. However, it does make programming with it much more difficult, okay? Because without non-standard evaluation in that previous example, it's going to be looking for objects called manufacturer, model, and highway, and it's not going to be able to find them, okay? Because it's not in your function and it's not in your global environment. So let's say we wanted to use dplyr to create a function that does basically like a crosstabs sort of thing, okay? So typically we would start by writing a function, like if we wanted to write a function to do this, we would start by solving it on a small problem, and we would generalize that to a function. So let's do it, okay? Here is the code, it's up at the top, that I'm giving you. So I've done the first part for you, okay? I have solved the problem for one specific example. So this is what the output should look like. So basically we have a data frame that is going to be passed. We have one group, two groups, and then we have some outcome here that we're going to summarize. Okay, so it's going to summarize some outcome by two groups, and that's going to be within some data frame. All right, so this is what the code looks like. And what I'm asking you to do is just generalize this code, and don't worry about non-standard evaluation for now. The purpose of this is really for it to fail, because it's going to fail. But try to write this as you would expect it to get this to work as a function. Okay, so 4 minutes, go. And we are going to be doing many of these coming up, so please do get RStudio running if it's not currently. Okay, was anybody successful? That would be my guess. Nobody was successful on Zoom, were they? Okay. This is what I would have expected to work if it were me, right? Function, data, outcome, group 1, group 2. And then I take, just basically copy and paste that code that I had, swap out data for empty cars, and then group 1, group 2, and outcome, right? Names from group 1, values from mean up there, okay? But this is what we end up getting. Is this a similar error to what you got? Okay, and notice what it's saying. Column group 1 is not found. Column group 2 is not found. okay? And that's because when we wrote it back here, we have group 1, group 2, right? And when we're using this function, we're passing the bare names just like we would with dplyr, but it doesn't work, okay? And that's because it doesn't know where to evaluate it. So it's looking for an object called group 1 that doesn't exist inside the function or in the global workspace. So the solution is to quote it and evaluate it in the correct space. So this is where rlang comes in, okay? This is the tidyverse version of non-standard evaluation. rlang has a bazillion different things that you can do with it, right? This is one of the most simple ones. And I'm introducing you to this one first, which admittedly is a little bit more difficult, but it sort of mirrors the process we were just talking about. And then I'll show you an easier way in just a minute, okay? So we start out by taking our output, our group 1 and our group 2, and we just quote it, okay? Within rlang, anytime you're quoting something inside of a function, you use enquote, okay? Inside a function, you're going to quote it, enquote, all right? So you quote those 3 things, and then to evaluate it, you use the exclamation point twice, okay? It's pronounced bang, bang, all right? So data just gets passed because that's an object, right? But then you're going to group by bang, bang, G1, bang, bang, G2. Notice G1 and G2 are the quoted versions of these things, okay? Then you're going to summarize mean is equal to mean of bang, bang, out, right? And then pivot wider names from bang, bang, G1. And now, lo and behold, it works, okay? And this is actually pretty neat now that it works because it works now just like a dplyr function that you have, right? And so I didn't show it here, but because data is the first argument, and I think there are other examples where we'll look at this, because data is the first argument, you can include this just in a pipeline like you would before, like data, filter, mutate, and then just say group means, and then pass the additional arguments there, and you'd be good. Okay? All right. An alternative thing that you can do that will get you out of the world of non-standard evaluation very often is you can pass the dots. So in this case, I say data outcome. I still do have to quote the outcome, but then I can pass the dots for the grouping factor. So then I say data group by ... and then summarize the mean is equal to bang, bang, out. Okay, and then I get something like that looks like this. An added benefit of this is that now I can pass as many as I want to. It doesn't have to just be 2, and it will group by all of those when it computes the mean. However, you might be looking at this and thinking, well, but that's not the same thing as before, right? Because I was doing a crosstab sort of thing. Now this is just the means, and that's correct. So in this case, passing the dots will not actually fully fix our problem if that is what we want. If we actually want that crosstab sort of thing, passing the dots isn't going to help us. But more generally, you should think about passing the dots in your function as a way to avoid non-standard evaluation if you can help it, okay? But there still is another alternative that we can use. So again, quote, evaluate, right? That's the basic structure. There is a newer, like maybe last year and a half or so, syntax, which is just double curly brackets that does exactly that same thing. It quotes and evaluates in the same spot, okay? So now I can actually basically do what I did before, which is just copy and paste my code. All I have to do though is all of my arguments. I have to wrap all of my arguments except data, because that's just the object. I have to wrap them in double curly braces. Okay, so this is the newer way to do it. and this is the way I would highly suggest that you do it. But I've included the other slides and the other discussion around that so that hopefully you have a conceptual idea of what's actually happening. And this will not get you out of every single problem that you will have. All right, so this works, as we can see down here, group means 3, right? And then I mentioned this before, but now we'll actually see examples of it. Because the data argument comes first, it is still now a pipe-centric function, and so it can be used just like it's a new function in the tidyverse. So we have diamonds, we can filter where the color is E, and then select a couple variables, and then call group means 3, and just provide the 2 grouping factors and then the outcome. Or I guess it's the outcome and then the 2 grouping factors. All right, caret cut clarity, and there we go. We get our table. Okay, so this is a table for just color E. Okay, so obviously, very clearly, right, the double curly braces is a lot easier. It's pretty simple, actually, even if you don't totally understand what's going on there. But the way that I've presented it is to get you to hopefully understand what's going on there. It's quoting and it's evaluating in the same spot. Okay, and again, that's going to get you out of most of the problems. I would estimate 80% of the time. It might even be a little bit higher than that, depending on what you're doing. Okay, but if you start programming a lot with the tidyverse, then there will be times that you're going to have to dig into Erlang and do different things. The only other one that I use a lot is called Sim, S-Y-M, and it changes things into a symbol. So you can have like a string that gets transformed into a symbol so that it can be evaluated. Okay. But this general idea of quoting and evaluating, you'll probably want to get pretty comfortable with if you're going to be programming a lot with the tidyverse. Okay. All right. 7 minutes. We're going to actually do this because we do have time. So I'm going to give you a full 7 minutes. And what I would like you to try to do is to write a function that summarizes any numeric columns by returning the mean, standard deviation, min, and max values. Okay. So what you should do for this is to use a data set. You could use diamonds if you wanted, for example, and then solve it on that data set, and then generalize it to a function. Okay, so this is the way that I've done it here, right? Where I have the data set first, and then the columns that I want to summarize next. Okay, so in my case, we have var. So notice depth is here, price is here, and table. Those 3 variables I've passed, those are all become rows of the table. And then we have mean, standard deviation, min, and max. Okay, so 7 minutes, give that a try. Try to write that function using the tidyverse. And you can use any of the approaches we saw. Okay, so I'm going to switch my share. And we're going to come over here. Okay, so if I say diamonds, oops, I need to load the tidyverse first. Then diamonds. It looks like this, right? And the ones that I was looking at was depth, table, price. If I just asked you, right, compute the mean of these things, that's pretty easy, right? We know how to do that. That's just, we would just go summarize, you know, mean depth equals mean of depth, etc. Right? And we could continue on like that, but that's not very efficient. All right. So what I would do instead, so there's a couple things that kind of make this problem a little bit difficult, but actually in this case, non-standard evaluation is not one of them. So you may have gotten tripped up on that, but this is how I would do it, okay? I'm gonna first select the variables that I want from diamonds, okay? And then I would pivot longer everything. Okay, when I do that, I get something that looks like this, right? Then I can say, all right, now group by name, and then say summarize mean equals mean value, right? Depth price table, there's mean. And similarly, you know, I could continue on with that. Standard deviation equals standard deviation of value. Okay, so let's just pause there for a second. Now let's say I want to wrap this in a function. All right, so I'm going to copy that code and I'm going to say summarize calls function. And I'm going to just ignore my arguments for a second. I know I'm going to have a data argument, but what else am I going to have? If I'm looking at this, right, the idea, so this is going to be data. The idea was that this would be any columns, right? So what I need to do is go ... and replace that select here with ... And that's as much as I need to do. Now I can do summarize calls, and I can do it on diamonds to make, oops. So let me go back to here, grab that. Right, and that gives me the mean and the standard deviation of those three. But I could also go to something else. Let's look at empty cars and go empty cars, MPG, HP, DRAT. And that works on there too. Okay, the other thing is because the data is the first argument, this is now a pipe-centric function. We can use it like that, and that works as well. Okay, makes sense? All right, so that is how I did it here as well, which I'll show you in the slides now. Passing the dots, that's the main sort of secret sauce here, and then also using pivot longer. Okay, and then you're just going to group by the var and then summarize everything. Okay, and it's pipe centric again, as I showed. All right. So let's now switch to an example with plotting. Okay, so let's imagine this is a very common use case that I'm interested in checking for linearity. Okay, so I'm interested in regression modeling, and generally linearity is going to be something I'm going to be concerned with, right? Is it linear or is it nonlinear in some way? And so one of the ways that I like to do this is to use ggplot and use geom_smooth twice. Once where I say method equals LM, and once where I say nothing. So the one where I say nothing, it's going to be one of two different types of fits, but it's going to bend with the data, right? The curve will. And the method equals LM is just going to be a straight line. So then I can compare the straight line to the curvy line and see if they roughly approximate. And if they do, I feel pretty good about my linearity. If they don't, I don't feel so good about it. Okay, so that's what I'm going to basically do. I want a function that produces both a linear and nonlinear fit displayed. Okay, optionally, we could show the data, meaning we could show points. Okay, so we could have a scatter plot sort of thing that has the points or doesn't have the points, depending on what you want to do. Okay, so here's one approach, right? I'm calling it check linear. I have a function, it takes the data as its argument, then x and y. We say SE, the standard error, equals true by default, and points equals false by default. Again, this is how you're going to specify default arguments. So this is not how they will always be. If you wanted to say SE equals true or SE equals false, then the standard error would not be there. But by default, if you don't supply that argument, it will be there. Okay. Then I'm building up the plot in layers here. So I'm starting with P, ggplot data, x, y. Then I say if is true points, So if points is true, then I'm going to add a point layer, right? Then if is true standard error, then I say geom smooth LM and geom smooth. Otherwise, so this is when it's false, I say geom smooth with SE equals false and geom smooth with SE equals false. Okay. And then very importantly, I put P at the bottom because that is what is returned. Okay. Anything that you see there that looks weird or wrong or incorrect? Okay, give me your confidence that this is going to work. Like, just hold up fingers. If you're pretty darn confident it's going to work, give me a 5. If you think it's for sure going to fail, give me like a 0 or a 1, and somewhere in between there. Okay, seeing, at least in person, a lot of not very confidence it's going to work. So why do we think it's not going to work, other than me asking you that it's not going to work?
X and Y should be in the like we should use the curly braces for that.
Yes, X and Y look problematic. That's very good. When we do this, sure enough, bill length millimeter not found. And so what we have to do is exactly what Javi just said. We have to wrap X and Y in the double curly braces. Okay. In this case, I also did a few other things. I just said geom smooth, and then I passed the dots here and here, right? So that in the function up here, it's data X, Y, and then points equals false. And then it's just ... which means any additional arguments passed to geom smooth, including standard error, right? So the standard error is true by default. So by just passing the dots, we get that, but we also get other things that we might care about in there. Okay, so now we do check linear penguins, bill length, bill depth, it works. Okay, we can add points equals true, yay. But because it's a ggplot object, we can also continue to add layers onto it if we want to. So here I've added a labs layer and then an additional theme to it, and it all works. So it's sort of like, this is really good, like sort of modular programming, right? You're building a plot, but it's within the sort of ggplot universe. And so you can continue to add layers to that plot just like you would any other ggplot. Okay. All right. I'm trying to decide currently whether it's worth continuing to practice in the slides or whether we should jump to the lab. What do you think? Would you rather continue to work all together like this, or would you rather jump to the lab and have the last 50 minutes for the lab? Let me just double check. I think so. Yes, we have. So this is, the rest of it is more examples and more like different ways of using it. We really only have one left. So maybe, I don't know, should we just do it? All right, we'll just do it. Okay, so building up plots. So we're going to create a function that calculates means and standard errors for every numeric column in a data frame. Okay, so that bullet has a lot in it, right? Means and standard errors for every numeric column in a data frame. So we know that the argument is going to be a data frame. And we know from there, we're going to have to subset that data frame to get only the numeric columns. And then we're going to compute the mean and the standard error from each of those columns. Okay, so that's a lot of stuff. We'll then use that function to create a plot. So first thing, standard errors. There is not a built-in function in R for computing the standard error of the mean. It seems very strange to me that there is not, but there is not. Okay, so it is just the standard deviation divided by the square root of n. So we can create that function ourselves very easily, right? You could have removing missing data be optional. I chose to not in this case. Okay, so I said function x not is .na, x Okay, so I'm removing missing data here, and then I'm just doing exactly what you see up here. Standard deviation of x divided by the square root of n, and the n is the length of x. Okay? So now we need to figure out a function to do what we said before, where we're going to take a data frame, subset it to only numeric, and then compute the mean and the standard error of all of those columns. Okay? So I'm going to use a similar process to what I did before. I'm first solving it on an individual function or individual data frame, which is penguins. So I'm taking penguins and I'm saying select if is dot numeric. That gets me all my numeric. So there we go. Good. Step one, done. Then I'm going to pivot longer everything, the names to vars, the values to val, and we're going to group by var. Okay. And then I'm going to summarize, compute the mean and the standard error. Okay. And there we go. That works for that data frame. All right. Try to generalize that code that we have on this slide to work on any data frame. Okay, so you're going to write a function from this code. All right, and you can test it on 4cats GSS cat because it has both numeric and non-numeric data in it. Okay, 3 minutes. Okay, give me a thumb gauge of some sort. Those of you on Zoom, please also through emojis or whatever you want to do. How successful were you? All right. Okay. All right. To translate this to a function, this is the approach that I would use. I take my df and I pass it here, right? But everything else actually just flows right through. I don't actually need non-standard evaluation at all. Okay, if we contrast this with over here, it looks pretty darn similar. Okay, and the reason is because all this is doing is taking a single data frame and the rest is going through. We're not actually selecting any columns, so we therefore don't need non-standard evaluation. Okay, so this is one where even without non-standard evaluation, it should just work. Okay. From here, we can then use it to create some plots. I've used this geom line range here, but it's so tiny that you can't even tell. It just looks like the point. All right. But here's one example. Okay. So from here, we could generalize this also to a function. Now, quick pop quiz. Do you think, and you just can think in your mind, you don't have to say out loud, if this is what we've done to create one plot, and we want to generalize this to a function, do you think that we have to use non-standard evaluation? Okay, have your answer in your head. Here's the answer. We have successfully avoided tidy eval entirely. Okay. And there you can kind of see my geom line range. Not so much there, tiny bit there. Okay, but you can see it works for other ones. Okay, so that is basically it for the slides. So overall takeaway, non-standard evaluation is complicated, it's hard, it's weird. So do not feel at all less than if you are confused by it. As I said, today is really to expose you to it and get you to understand that if you're trying to program with dplyr or ggplot or tidyr or any of them, and you run into errors with your code, it's very likely that it's an rlang issue, like a tidy eval issue. So the first thing you should do at that point then is look for columns. Are you calling out specific columns? If so, then you should be wrapping that in the double curly braces, okay? As I said, that'll get you out of trouble probably 80 to 90% of the time. If that's not helping you, then it might be some other non-standard evaluation thing. But always go back to your test case and make sure it's working there, because you don't want to end up in a situation where you're digging into non-standard evaluation really hard, going into some rabbit hole, and it turns out you just had a bug in your original code that was creating the thing, right? There are multiple ways that you can go about this. Sometimes some are easier than others, and the best is to try to avoid it altogether. So if you're going through and you're trying to write a function, try to avoid it if you can, and if not, then try to use double curly braces. Okay. All right. So I mentioned this at the top of the class. I'll just mention it one more time. Next class, we will have our intro to Shiny. The one after that, we will have one more lecture on Shiny. It will be a lot of the same sort of stuff both times, but we'll be talking about Shiny and then Shiny dashboards. And then the class is over, basically. Okay, so your because we have week 8 and 9, and then week 10 is a holiday. Okay, so your final project will be due week 11. If you happen to be done with it earlier, get it into me. I'll get it done as soon as I can. Okay. All right, let's look at the lab together real quick. All right, lab 3. So the first part A, foundations, these are just sort of look through the slides and find the answers sort of things, just questions. So name and describe 3 fundamental components of a function, and describe 3 different ways functions can be stored / applied, and an example of when you might want to use each version. Okay, then the mean is defined here, right? So sum some stuff and divide by the number of things. The first question is in part B is write a function that calculates the mean, but your function is going to remove missing data by default. Okay, then I want you to compare it with base mean and make sure that you get the same results when na.rm equals true. So that's actually the second part. So first part is writing the function. Second part is testing your function to make sure it's the same. Then for part 3, I've given you a couple of different, so 3 different lines of code that do some stuff. And I'd like you to turn each of them into functions and specifically give them meaningful names. Okay, so I've kind of told you what they do, but you want to transform those into functions and make those functions have meaningful names. Okay, 4 and 5 are quite a bit trickier. So my guess is you'll get up to number 4 or 5 pretty quick, and 4 or 5 will be more challenging than the rest of the lab. 4, write a function that takes a data frame as its input and returns a data frame with it as its output, but only the numeric columns. Okay, you can choose to use tidyverse or not on all of these. Yep. Yep, that's right. So you're going to have a data frame as an input, and it's going to return the same data frame, but with only the numeric columns. And then for number 5, write a function that uses this function. So you write the function in number 4 that selects only the numeric columns. You're going to use that function inside of a function that you write on number 5 that returns a data frame with the mean and standard deviation of each numeric column. If the columns are omitted because they are non-numeric, print a message stating the specific columns that were not included. So that part of it might force you to go back to what you were doing in number 4. Okay, so you'll have to think about how you want to do it, but that's the general idea. Okay, any questions on that? You have a little over 30 minutes left in class to work on it here if you want. Those of you on Zoom, you can hang out. I can put you in breakout groups if you want, or you can just sign off. It's up to you. Okay.